Hello, F-sharp. Welcome back. We continue our journey of writing an extremely high-performance dictionary just using F-sharp. Where we left off last time was looking at some light metaprogramming that we can do with the dotnet framework. We saw that the dotnet framework is very intelligent when it compiles its code. And if it sees that, oh, I will never need this code due to type information or some type of branching logic, it'll just eliminate that, which allows us to potentially have additional inlining, giving us better performance. Because at the level of performance that we are working at, having additional stack frames can actually slow us down. What you're seeing on the screen right now is the results from our previous benchmarking. What we're seeing is that for our dictionary, which in this case is the fast type branch method, we are faster for all cases where the key type is an integer. And then for string, we're faster at 10 and 100 keys and also at 1,000, but we're slower at 10,000. I'm kind of throwing out the results for the 1,000 key count because what we see here is that for the built-in .NET dictionary, that there's some type of allocation going on here. Now, why exactly it is doing that? Probably something to do with strings. I haven't been able to zero in on it because it's intermittent. At the end of the day, for where we're going though, this isn't going to matter, which is why I'm kind of glossing over and not really digging into that piece. But what we're wanting to do is figure out, okay, how could we potentially go even faster? And we're going to start using some new memory layouts to hopefully give us faster performance. Now, first, what I want to do is kind of review where we are at with our memory layout. And to do that, it's almost always easiest to draw that with a picture. So right now we have our dictionary, and we know the way dictionary works is that we have some backing array. Inside of this array, we have buckets. And when you go look at literature and you read, you're going to see that these different slots in the array are referred to as buckets. So when we want to look up a value in our dictionary, what we do is we take the key and then we compute a hash code using that key. And then that hash code then maps to a bucket index. And that's going to be one of these buckets. Now, what is inside of these buckets inside of our array? Well, right now, what it is holding is a reference to an F-sharp list. And so when you go and look this up, you're going to go somewhere out, and now we're on the heap. Well, technically, the array is also allocated on the heap, but somewhere on the heap, there's an F-sharp list. And then we have an element in that list. And inside of that element, it has another reference to our entry type. And that entry has the key and value inside of it. And this F-sharp list could potentially have a link, because it's a linked list, it could have a link to another element in that list with potentially another entry and then potentially another link and on and on. What you're seeing here is that there's a lot of references and we're bouncing around a lot. And if we were working in the C world, they would be saying like, oh, we're pointer chasing at this point. Now in .NET, we're typically not working with raw pointers. We can, and we are using pointers a little bit for our string hash code computation, but typically not. And so we would think of this as like, oh, I'm just following references all over the place. And so what that means is like, oh, I need to look up a value, but that value is actually a reference somewhere else. So I need to go load that into memory. And so all these loads are potentially huge performance bottlenecks, because often what is the bottleneck in the performance of our algorithms is the memory bandwidth. It's how quickly can we get data in and out of caches. And what we want is for all the hot data that we are going to be working with, we want that to always be in cache so that we don't have to pay the penalty of going out to main memory to fetch it, because that is orders of magnitude slower and be a huge hit to our performance if we're having to do that all the time. And so This is what we're using currently, and as you can see, we're already getting some relatively good performance with it compared to the .NET dictionary. But again, we are facing this challenge, like how fast could we possibly go? Now, again, this is where I iterate. All of this is inspired by a talk I saw on YouTube at a C++ conference by Multi. And again, the link is in the description below. If you haven't seen it, I strongly suggest that you go and watch it. It's inspiring. So inspiring, in fact, I'm doing this series. So I'm taking from his playbook and the things that he has used. And so I always want to cite my sources. So what we're going to do now is, instead of having our array, the entries in our array be references to linked lists somewhere out in the heap, we are going to embed the head of the list inside of this array. And so what will that look like? So if I move down, so now we still have our behavior where we have we have our key, which then gives us a hash code, which then gives us a bucket index into our array. And I am going to say, like, okay, now when I go to a particular bucket, what is in there? You might remember before it was a reference somewhere else out in the heap. But now what we're going to do is say, like, no, we're going to make what is inside this array a struct, so that the data is going to be in the array physically itself. So if I zoom in here, so notice I'm not pointing somewhere else in the heap. I'm trying to signify that I'm like zooming in on this. It is an entry. And that entry has a few different things in it. It has the key for that entry. It has the value. It has the hash code, so that we don't have to recompute hash codes, because that would absolutely destroy our performance. And then, and I should call this a struct. This is a struct entry. And then it has a ref entry. What do I mean by that? What is this? This is how we deal with collisions. So let's say we have many keys and values that we're wanting to store in our dictionary. It is entirely possible for keys to compute hash codes, and those hash codes then correspond to the same bucket index into our backing array. So like, hey, we got a bunch of values and they're all mapping to 10, the 10 bucket index. So how do we deal with collisions? Because we cannot store them all there. They're different keys and values, but they're all mapping to that same location. And every dictionary has to have some strategy of dealing with it. The way we have dealt with it to this point is this, where we say, like, you know what, you're going to go to an entry here, and then that entry is just a linked list. And so we can just add entries to this linked list. Now what we're saying, like, hey, this is not going to be a linked list. We're going to inline. I know inlining is not technically the correct term, but I want that data to be in the array so I don't have to pay the penalty of doing an additional reference lookup. So I'm going to embed one key value pair in the array. And if there are additional keys that map to the same bucket, what I will do is I will then have a linked list off of that struct entry. And so the way what this looks like, and I'll kind of draw an even more zoomed in, yeah. I think this is okay for now, because we're going to go look at the code and you'll see what this means even more. And so this ref entry, this thing is actually a reference to somewhere else out in the heap. And so this would be a ref entry. My apologies for the handwriting. This is why we're going to look at code here in a sec. And that ref entry has the key, the value, it has the hash code. And what it could also potentially have is another ref entry. And so this is that kind of linked list idea, like, hey, I have a ref. This struct entry is embedded in the array, but it also has a ref entry for the other possible keys that are mapping to the same bucket. And that ref entry could end up just being what is essentially a linked list. So let's go look at the code of how we would implement this. So I'm in the fast dictionary test solution. I'm looking at the fast dictionary test project. And now I'm going to look at what I'm calling embedded head. And so this is the idea of embedding the head of the list into the array, which is the backing store for our dictionary. And now I'm going to define these two new types that we're going to use. One, let's start with struct entry. This is our struct entry. This is the entry that is actually embedded into the array itself. So the idea is I look up, and I don't have to chase a reference somewhere else on the heap because that first key value pair is going to be right there in the array. And most of the time, if you have a good hashing function, most of the time, only a single key is going to map to that bucket. And so this is optimizing for the best case scenario or the expected case scenario. So in here, we have the hash code, the key, the value, and what I'm referring to as the tail. So you can kind of think of this as, this is essentially a linked list, but the head is a struct, so I can like really put that data where I want to put it. It's not just allocated on the heap, it is in our array. And so when I want to go look up an entry in my dictionary, I'll come to a struct entry, I'll check the hash code and the key, and if they match, great, return the value. If not, I now have to search down the tail, and the tail is made up of reference entries or ref entry. Again, it also has hash code, key, value, and it has the possibility of having a tail itself. Now, why? There's a lot of mutability going on here. Yeah, and that's for the scenario where I'm constructing the dictionary. I'm taking in a sequence of keys and values, and I'm utilizing mutability as I build the dictionary. But at the end of the day, I could then return that data wrapped in a data structure which doesn't support mutation or adding or removing entries. And that's how I can get my read-only dictionary from this result. Because if you remember from the very beginning, the whole reason this started is because I saw that the performance of read-only dictionary versus dictionary was much worse. And I was like, why is that the case? That is unnecessary. I understand why now, but for my use cases, I need a high-performance read-only dictionary. So here we are. So I utilize mutability when constructing the data structure, but afterwards, I don't allow mutation. So struct entry for the entry that's in the array, and then reference entries for the tail coming off from it. Now that changes the code, and we're not going to go too deep into it in terms of like, hey, how do I add to this? But I will just show you what it looks like for adding a struct entry into here. I'm going to go ahead and collapse that. And the way it works now is I have to check some additional conditions. And so the logic around inserting a key value pair into this dictionary is now more complex. And so what I do is I compute that hash code. I then say, okay, compute the bucket index that hash code would map to, and then go get that entry. And this entry is an instance of our struct entry. I'm using byref. I'm returning it byref so that I can look up the values. Do I need to do this? No, but the reason I'm doing it is because I'm returning this by reference, because if I didn't return this by reference, this entry is a struct now, that first entry into that array. And so if I just did the default thing, well, first of all, I wouldn't be able to update any of the fields in it, but it would actually be returning a copy of that data because a struct is a value type. And so it would just be like, hey, copy whatever data is there and return that from the array. That's not what I want to do. I want the actual that actual piece of memory itself, which is why I'm using byref here. And what I do for, well, I'm going to go ahead and skip to looking up. Well, now we're talking through adding. Let's talk about the logic of it. So I'm returning that memory by reference. I'm checking, is there anything in here already? And I'm using a hash code value of -1 to indicate like, hey, there's nothing in this bucket. And if it's empty, then I can go ahead and add the entry. If it's not empty, I got to check, does the hash code match? And are the keys equivalent? If so, I will just update the value. And let's say, yes, there is something in there. It's not the same thing. So now I need to add it to the tail. And this is where things get a little bit spicier for the F# side of things, because in F#, we typically don't have to think about nulls very much. But in this case, I am utilizing nulls and null addresses to my advantage, which means I have to check, hey, is this referencing a null or not? Because if you remember from up here, the default value for a reference type, which is what this is getting. So when I create an instance of a struct entry, I'm saying the tail is an unchecked default of ref entry. Well, this is a reference type. What is the default value for a reference type? It is a null address. It is a nowhere. And so down here, when I'm adding it, I got to make sure, hey, is this actually pointing to something or not? If it's not, I can just create a new instance of ref entry and have the tail now point to that reference. Otherwise, I now have to kind of start traversing down that linked list and finding where the end of it is and then adding it on. So that's adding. Now let's go to looking up. And again, I'm just going to review the structy version of this. If you want to understand like why we have struct versions of functions and why we have reference versions of functions, I strongly encourage you to go watch the previous video on the metaprogramming, because that explains why. But essentially has to do with performance and optimizations that the .NET runtime can do. So when I want to get a struct, when I want to get a value out of here, I'm given a key. Again, I compute the hash code. I then compute the bucket index that hash code maps to, and I check that entry and say, okay, which entry is that? And I potentially could have done this by ref here, but I haven't. So that might be a potential performance improvement. I go look that up and I say, hey, is this, and this is me hoping that the key is in that first struct entry that's in the array. And if it is, I don't have to do any more reference lookups somewhere else on the heap. So this is what my ideal scenario is. I'm checking, does the hash code match and are the keys equal? If so, just return the value. And this is going to be the predominant case. This is what will happen most of the time, because statistically, the way, if you have a good hashing function for your keys, and then that you have a good function for mapping the hash codes to entries in your backing array, you should typically only have one, maybe two entries per bucket in your backing array. Now, there are different strategies around when you resize. Right now, we're using a very naive resize strategy of once we get over 75% full, we will resize, which might be a little bit too aggressive. But still, at the end of the day, this is the most likely code path. If it's not here, we then have to go start searching down the tail and looking up entries. And so we would ideally don't want this to happen, because now we're going to start chasing references. Like, okay, look up this entry, look up this part of the tail. Is it this one? Okay, it's not that one, but does it have more tail that I have to keep searching down? Like, okay, so you end up searching down this linked list. We really don't want to do that. So we're hoping that this strategy of having a struct as that entry in the array is going to save us a lot of additional lookups for when potentially multiple keys are mapping to that same bucket. And when we run this benchmark with this strategy, and it's called the embedded head strategy, we see that for key counts of 10 and 100, it's essentially the same, 48 microseconds and 44 microseconds, 41, 49, not that big a difference. What's interesting though is notice here for our previous version, for 1,000 entries, it was 87 microseconds. Now for 1,000 entries, it's 66 microseconds. For 10,000 integer keys, it's 119 microseconds for our previous dictionary, 88 microseconds for our new dictionary. And so the performance improvement that you're seeing is the reduced need to immediately go to an entry in the array and then go searching off. And so if we start thinking about like, why would we see such a performance improvement at 1,000 and 10,000 entries, but not at 10 and 100? Why are 10 and 100 entries essentially the same performance, but much better for 1,000 and 10,000? That, think about that. And I would encourage you to like pause for a moment and just kind of think through about what we just went over in terms of structs, references, memory layout, to try to develop an intuition about like, okay, why would it not help the small dictionaries, but it would help the big? So pause. Okay, now that you've spent some time thinking about it, what's going on? When you have very few entries, it is very easy for the CPU to keep all of the data in cache. The array is in cache, and all the elements of the linked lists that the array is pointing to are all in cache. And so the performance difference is essentially zero because all the data is in cache. You're never having to pay the penalty to go farther out to fetch data. When you get to more entries, it is more difficult for the CPU to be smart about what data needs to be in cache. And when you have linked lists, those entries are potentially spread out all over the heap. And so it is much more difficult for the CPU to reason about what data needs to be in cache or not. It knows it needs the array, but the array could be pointing all over the place. When that first entry is a struct, you know it's in the array. And most of the time, that first element is the one you want. And so you are dramatically increasing the probability that the entry that you are looking for is in cache. That is the big deal. And part of why when we look at string and we go all the way to 10,000 entries, we see, oh, well, the dotnet dictionary is better and ours is worse. I mean, why? Like, we don't see a big boost here because the string itself is a reference type. And so again, stuff's getting spread out and the heap could be a big jumble. And so we're not getting as much benefit because even though that first entry is in the array for strings, that entry, that key is still a reference somewhere else. We're still going to pay the penalty of having to go look up, okay, where is that string in memory? And so we don't get the same level of performance boost that we do when we have struct because everything is there. All that we know that data is in the cache. And so that is the most significant reason for why embedding that first head, that first element in the array is giving us a big performance boost. Now, that's great, but we can do better. There are more strategies that we can use for dealing with collisions in a dictionary and for how we lay our memory out. So do not be discouraged. We actually still have quite a ways to go. But I'm hoping to kind of help you develop that engineering intuition to understand how the CPU is thinking, how F# is thinking, so that you can come up with these solutions on your own. I hope this has been helpful for you. What would be helpful for me if you left a comment asking clarifying questions or things that you want me to look into more. I really enjoy creating these videos and helping people. Like I want people to grow. I want to grow the F# community, and I want to provide content for new F# people, but also people who've been writing F# for a while and are looking to take their code to the next level. So thank you so much for spending some time with me. I've really enjoyed it, and I hope it's been a blessing to you. You have a good day. Bye-bye.